Science! Let me teach you a thing or two about gravity. Boys and girls, have a seat. Let me tell you a little bit more about my friend, one of the founders of gravity. This fine gentleman, his name is Sir Isaac Newton. He lived about 350 to 400 years ago, and he is one of the founders of modern day physics. He helped us understand quite a bit of things, and actually there's a very interesting story about how an apple fell from a tree and almost hit him on the head, and that is how he got interested in being a scientist and learning more about physics. Interesting thing about the way he described physics and gravity is that time was constant, time never changed. And that actually makes sense from what we see day to day. I can't go backward in time, and I can't speed up time. But that's where things got interesting and changed. Because along in the 1700s and 1800s, they realized that his formulas were not always complete, and more needed to be learned about the universe. So along came this fine gentleman. Does anybody know who this gentleman might be?
It's you!
Close, but it's not really. It's Albert Einstein. Albert Einstein helped correct some of the changes in Newton's laws and the things that weren't fitting together, and he realized that time actually can be changed. So we have 3 dimensions, length, width, and height, and now a 4th dimension, which is time. And that was wrapped together into a thing called space-time. I want us to learn a little bit more about space-time because it is really cool. Voila! We have space-time. So this is what Albert Einstein and his colleagues came up with. They came up with the idea that the universe is actually like a fabric, and it can be actually stretched or changed when you apply mass. You had those balls earlier. Why don't you go put those balls on there and roll them and see what happens. Notice, see how they're rolling close to each other? Notice how they're deforming the fabric. Now, if I get a heavier ball, put that there, what happens? Yes.
It goes in the middle and makes waves.
Exactly, and so Albert Einstein shows that the more mass that you have, the more gravity starts to pull the objects in. So gravity is this change, it's this dipping in the fabric that causes objects to go closer together. Now, I want to bring up an important point before we get too far along. In the universe, as we think about it, this is what only about 5% of this can be seen. There's about 25% that can't be seen, and that's called dark matter. And so dark matter and what we can see matter help make up our universe. But I also want to bring up one other interesting point. I want you to remember dark energy. So everything in the universe, 70% is dark energy. And that's almost like anti-gravity. And that will be important here in a second. So if we have gravity, we must have anti-gravity. So this is getting exciting. So the more mass, the more space-time is deformed, the more gravity pulls objects down toward each other. So, take the balls back. Let's go and put that over here. And now, let's go and take an even heavier ball. Look at that. Now, go ahead and roll your balls over. See what happens. Oh, look at that. See how fast it moves toward it? So something that's lighter or less mass gets pulled to something that's heavier mass because of how much it's changing or warping space-time to fabric. Isn't that pretty cool? All right, let me give you that there. Now, let me go ahead and let's pretend that we're in our solar system. What's the big bright object in the sky? Yes.
The sun.
Yes, the sun. So the sun is probably going to be heavy or light?
Heavy.
All right, so if it's really heavy, then the planets would probably be lighter. And you see how they go around? Watch how they circle. They're circling the sun. And it's because the gravity keeps pulling them around, pulling them around, pulling them around. We have a solar system. Voila. Isn't that pretty cool? Now, what would happen if we had a black hole? Does anybody know what a black hole is? Yes, young lady.
It's where mass is so heavy, not even light can escape.
Oh, you must be a budding young physicist. Exactly. That's exactly it. Now, if I had more mass and more mass and more mass and more mass, eventually the fabric gets so stretched that you need such amazing speed to leave that not even light can escape. And Einstein and others realized that light is the absolute fastest that anything can move. And so in a black hole, if you get sucked into a black hole, you cease to exist, you get crushed by all the matter, and there's a thing called a singularity, and that's something we can talk about for another day, but it's pretty awesome. So if you have a black hole, everything gets sucked into it. You gotta be careful. Now, all right, let's do this again. Now I wanna pretend that this is Earth, and this is the moon. Now, the two aren't pulling each other, but you can see how they're changing the space-time fabric. Imagine if you were a spaceship that had taken off from Cape Canaveral and was trying to get back from the moon to the Earth. Notice how it's going from the moon to the Earth. There's a thing called a trans-Earth orbit or translunar orbit. And because of the way gravity and the deforming of space-time is, you can see how as the spaceship gets further around the planet, it gets a big whip of energy, and that actually helped us get to the moon and back, and you didn't have to burn all that energy and fuel. Isn't that pretty cool? So you can use gravity to be your friend as well, and get you to the moon and back with less energy. Now, let's go back to the universe for a second. I showed you before how we could set up our own solar system. Now what I'm going to do is I'm going to take it, let's say in the beginning, the theory is when all the planets were first starting to revolve around their sun, there were some going right and some going left. You can see what happens if that happens. Oh, there we go. So eventually some of them start to cancel each other out and they knock out, and eventually you get most of them going in one direction. Isn't that pretty cool? All right, now we had talked about space-time and how it's a fabric, and how the more mass you have, the more it deforms, and that creates gravity. We talked about black holes and how black holes have so much mass that not even light can escape. We talked about the translunar and trans-Earth orbits. The last thing I want to talk about is anti-gravity. Now, I told you that of everything in the known universe, 30% is matter and 70% is energy. And of that 30%, we can only see 5% of all that matter. Now, does anybody know, is the universe expanding or is it shrinking? Yeah.
Well, I think it's expanding.
It is, excellent. So if the universe is expanding, that would seem to go against our model here, right? Because according to my model, everything should be kind of falling inward because of gravity. That's the mystery of black energy or dark energy. With dark energy, it's antimatter. So, young friend of mine, please go underneath the table. I want you to go underneath the table, go to the middle, and I want you to push your hand up right here in the middle. Right, keep pushing, keep pushing, keep pushing. So, dark energy, there we go, pushes things away, and that's anti-gravity. So when you have anti-gravity, that actually lets the universe continue to expand. Go ahead, you're good now, thanks buddy, go ahead and relax. So anti-gravity or dark energy pushes things away, which lets the universe expand, whereas gravity's natural tendency is to actually pull together. So, pretty cool. You didn't think you knew all that about gravity, did you? Well, I hope you enjoyed this lesson. I had a great time teaching you about gravity and space-time, and now I would encourage you to watch some really educational videos about this because it's pretty fascinating.
Cool.